So we have said that the magnetic field of the sunspots is very important. So why is that important? Well, because there's a lot of magnetic energy. Remember, these magnetic fields are enormous. The magnetic fields of the sunspots can be vastly bigger than the magnetic field of the Earth. And so that makes this a huge magnetic field. But it's also huge. If you look at some of these prominent sizes, that gives you an idea as to how big this bubble of magnetic field is, and it's vastly bigger than Earth. So that's an enormous amount of energy. In physics, when I do the second semester physics, we talk about this magnetic energy. And we say this little u right there means the energy density. That's the energy per volume. So that's how much energy there is in a certain amount of volume. It's equal to, the B stands for Biot field, or the magnetic field. And so the magnetic field strength squared divided by 2 mu naught. Mu naught is a constant of nature called the permeability of free space. So that's just a constant. So basically, if the magnetic field increases, the magnetic energy increases as the square of that. So if the magnetic field doubles, then the energy density is 4 times bigger. If the magnetic field is 10 times bigger, the energy density is 100 times bigger. So it gives you an idea about the enormous amount of energy that is in there, in that magnetic field. So that magnetic field arching through the surface of the sun, where the sunspots are, that has this phenomenal amount of energy in it. Well, okay, so all this energy is there. So what? I mean, the energy's there. How do you get the energy out of there? Well, that's something called magnetic reconnection. Okay. And you actually probably use this all the time unless you have a diesel vehicle or you ride a horse. Okay. To get sparks in a spark plug, and forgive this, this is an ancient sort of a picture here. I couldn't find a modern picture that showed you what I really wanted to show. Okay. And that is the ignition coil here. Okay, so under the hood of your car, you've got this thing that looks like a Coke can, okay, and then wires that run to a distributor, and nowadays instead of mechanical distributor like in this picture, you have a electronic distributor. But then the wires, the spark plug wires, go to each of the spark plugs. Okay, now the problem is, to get a spark, you need thousands of volts. You need a couple thousand volts at least to get a spark. On the other hand, you got a 12-volt battery. And so how do you get a couple thousand volts out of a 12-volt battery? Well, what happens is the electric current runs through the ignition coil, okay? And the coil is basically, well, a coil. Okay, and so that as the electric current runs through there, it's like an electromagnet. So it creates a magnetic field in there. A magnetic field that's a teeny tiny fraction of the strength of the magnetic field in a sunspot. And then when you break the connection, the current momentarily stops. All that magnetic energy has to go somewhere. So the magnetic field lines reconnect, and they dump the energy into a voltage spike. That voltage spike, then the distributor is what just sends that to the individual spark plug. Okay. If you don't believe me, then what you can do is, while the engine's running, lay one hand on the fender and reach in there and grab a spark plug wire. You generally don't ever do that again, because you discover 2 things right away. First of all, you discover that yes, there's thousands of volts inside the plug wire, and B, the insulation's not perfect. And so you never do that again. But in fact, that's why you have to change plug wires now and then. In older cars, if you actually look under the hood at night, you see little flashes of sparks all over the place under there from microscopic cracks in the insulation of the plug wires that you don't see in the daylight. But that's magnetic reconnection on a small scale. So on the sunspot, though, you have these magnetic field loops that are coming out here. And as the magnetic field loops come out, then this is a vastly stronger magnetic field. It's a vastly bigger area, bigger volume than something the size of a Coke can, because this is like vastly bigger than Earth, vastly bigger than Jupiter. And so what happens is that when it reconnects, you release an unbelievable amount of energy all at once. This huge amount of energy released all at once. How much energy were you talking about? Well, imagine taking every nuclear and thermonuclear device ever created on Earth and detonating them simultaneously. And then multiply by 10. Okay. That's average as to what this does. That's an unbelievable amount of energy. And when you release all that energy in one spot, what happens is this is called a solar flare. And that solar flare then, releases all this energy into basically what's going to be the chromosphere and the lower corona. And so this energy actually causes the gases to accelerate at close to the speed of light. When they accelerate at close to the speed of light, they slam into the gases that are above. This is actually an interesting thing, when you have charged particles, because you've actually ripped these atoms apart. You've ripped them into protons and electrons. When charged particles suddenly stop, they give off vast amounts of X-rays. This is called bremsstrahlung radiation. And this bremsstrahlung radiation was actually a big deal in the old tube TVs and computer monitors. What happens is that the way the tube TVs worked, or the way the computer monitors worked, was that you had a beam of electrons moving at very high speed, slammed into the front of the tube where the pixels were and lit them up. Well, when they stopped, they actually produced enormous amounts of X-rays. They actually realized that early on that people sitting in front of computer monitors were actually getting more X-rays than X-ray technicians were getting. And so to limit that, what they did was they started putting lead into the glass to block the X-rays. So old tube TVs and old computer monitors had enormous amounts of lead in them to protect the users. Okay, that's why technically it was illegal to throw them away. To dispose of them, you were required by law to take them to a proper electronics disposal site because they were required to be treated as toxic waste. Now most people didn't realize that, and so they just threw them away. Okay, which means that there are landfills out there contaminated with lead leaching into the groundwater. But that was necessary because of all the X-rays produced. Well, these solar flares also produce vast amounts of X-rays. And so the vast amount of X-rays then start flying towards Earth. That actually affects us. We can actually ionize the upper atmosphere with all this blast of X-rays. There have been incidences, for example, in which the astronauts in space, during a solar flare, they got a massive dose of X-ray radiation. The flares can happen where the sunspot magnetic field is. So back in 2010, on the left over there is an ultraviolet image of the sun because this got super hot and flared in the ultraviolet. And on the right is a visual image of that same day. And if you notice on here where that flare is, where the bright flash is right there, that's the flare, there's nothing corresponding right here because the sunspots had already faded away. But the magnetic field was still twisted where the sunspots were, and when the magnetic field untwisted, that gave rise to the flare. Now, we can actually sort of predict this. We can actually look at the magnetic field of the sun, make a magnetogram on the surface of the sun, and measure how active how twisted the magnetic field is, and how likely it is to instigate a solar flare. We can detect this has happened because we have satellites orbiting the Earth. And when it happens, we rate the solar flare. And so we rate them by how much X-rays. So an A-type flare, B-type, C, M, X. Now, each of these is 10 times before. So each line is 10 times bigger. So if you go up 2 lines, rather than going up 20, that's 10 times 10. So it's 100. 3 lines is 1,000, 4 lines is 10,000. And so this is a measure. It's the GOES satellite. It's a weather satellite that it monitors what we call space weather. and it monitors these X-ray flares. This was back in 2001, and you saw bam, 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 bam flares. So these were M flares, which are moderately large flares. I mean, an M flare is substantial right there. Okay, and then this up here is an X flare, which is a huge flare. And then we had a little small M flare here, and then a bigger M flare, then an X flare, and a whole bunch of little bitty C flares. 2007 we're at solar minimum. Okay, and so 2007 was another solar minimum, and you notice there's like virtually nothing happening. And so this is current data right here. In the intervening years they've changed the data output, but I just ran this, so this is the data as of October 12. And you notice that there's a couple. What we discovered, there's actually a couple of sunspots on the surface of the sun, and they are making these little minuscule A-type flares, and that's the only thing that's happening. A-type flares like next to nothing. It's just basic standard sort of radiation from the sun. So we don't really worry about A-type flares. That's a picture of the sun in 2019. Notice there was nothing much there. Deep solar minimum. This is a picture from October 12th of this year, and there's two small sunspot groups. There's two very small sunspot groups on the sun, and those are the ones that are giving the magnetic activity. In fact, this is actually a magnetogram from the SOHO spacecraft, which is a European spacecraft orbiting Earth, staring at the sun. And you can see these two sunspot groups right there in magnetic field. And so that one right there is the one that's actually got the twisted magnetic field, making those little tiny flares.